Have you ever wondered how your computer can possibly juggle a dozen different apps, a video playing, and a huge file downloading all at the same time without just collapsing into a total mess? Well, today we're going to pull back the curtain and look at the invisible traffic cops inside your operating system that make it all work. We're talking about synchronization and what happens when it all goes wrong, leading to the ultimate system gridlock, a deadlock.
Hey, just a quick heads up. This whole topic builds on some really core ideas we've covered before in our operating systems playlist. So if you're just jumping in, you might want to go back and check those out first to get the full picture. All right, let's get into it.
Okay, so let's start with a really basic question. Inside your computer, right now, you've got multiple processes whirring away. Your browser, your music, the OS itself. But what happens when, say, two of those programs try to change the very same piece of data at the exact same microsecond?
What you get is a situation called a race condition. It's kind of like two people running to update a number on a whiteboard. The final number you see depends entirely on who got there last. And in a computer, that's not just messy, it's a complete disaster waiting to happen, leading to corrupted data and bugs that are impossible to track down.
And here is a perfect example of what I'm talking about. On the left, you can see both processes grab the initial value, which is 5, before either one gets a chance to save their update. So they both add 1, and the final value is 6. Totally wrong. To get the right answer, 7, you need one to finish its business before the other one starts, like you see on the right. The big question is, how do we enforce that?
To stop this chaos, we have to designate a protected area of code. In computer science, we call this the critical section. You can think of it like a room with a key, and inside that room is the shared data. The golden rule is simple. Only one process gets the key and is allowed in the room at any given time.
So how do you actually enforce that one-at-a-time rule? Well, one of the first ideas was kind of like taking a sledgehammer to the problem. Just disable all interrupts in the computer. It basically freezes time for every other process. But yeah, it's a terrible solution. It's wildly inefficient, and it's totally useless on the multi-core processors we all have today.
Another failed attempt is a technique called busy waiting, or sometimes you'll hear it called a spin lock. This is where a process literally gets stuck in a loop, just asking over and over and over again, is it my turn yet? Is it my turn yet? How about now? It wastes a massive amount of CPU power doing absolutely nothing useful.
So these early methods were, pretty clumsy. The real breakthrough, the moment that changed everything, came in 1965 from the legendary computer scientist Edgar Dijkstra. He came up with a much more elegant solution.
He called his invention semaphores, and the idea is just brilliant in its simplicity. This shopping analogy explains it perfectly. Think of the store as the critical section, and the semaphore is the limited number of shopping baskets. To get in, you have to grab a basket. If they're all gone, you don't just run in place. The OS puts you to sleep in a nice, orderly queue. Then, when you're done, you return the basket, and the OS wakes up the next person in line. It's just so efficient and elegant. Now, semaphores were a total game changer, but they still required the programmer to be really careful and manually manage everything. This, of course, led to the next step in the evolution: monitors. Monitors are a higher-level tool that's built right into programming languages like Java. So instead of you having to remember to lock and unlock, you just declare a piece of code as synchronized, and the language handles all that tricky stuff for you automatically. It's just way safer.
So awesome, we've got these great tools to manage multiple processes. Problem solved, we can all go home, right? Well, not quite. It turns out that the very act of locking resources to prevent race conditions creates a brand new and really dangerous side effect.
And this brings us to a whole new kind of puzzle that can freeze an entire system solid. Just imagine this. Process A has locked resource 1, and it's now waiting to get resource 2. At the exact same time, Process B has locked resource 2, and it's waiting for resource 1. What happens next?
You've just created a deadlock. It's sometimes called a deadly embrace, which sounds dramatic, but it's true. Both processes are now stuck in a circular waiting pattern, completely unable to move forward, and they will wait forever unless something or someone intervenes.
And you can see exactly how this trap springs shut right here. It's a simple 4-step path to disaster. Each process grabs one thing, then tries to grab what the other one has. The result? A standoff that has no logical end. It's a permanent system gridlock.
We can actually draw a picture of this problem. It's called a resource allocation graph.
You draw an arrow from a process to the resource at once, and when those arrows end up forming a closed loop, that's the telltale sign of a deadlock. The system is literally chasing its own tail.
Now, a deadlock isn't just random bad luck. It can only happen if 4 very specific conditions are all met at the exact same time. Resources can't be shared, a process is holding one thing while waiting for another, you can't just take a resource away from a process, and you have that circular wait we just talked about. The key thing to realize is, if you can break just one link in this chain, you can prevent deadlocks from ever happening.
So, if those 4 conditions are the cause of the problem, they also give us a pretty good roadmap for how to solve it.
And that gives us a whole toolbox of strategies. We can try to prevent them by designing a system where one of those 4 conditions just can't happen. We can try to avoid them with smart algorithms. We could even let them happen, but have a plan to detect them and then recover. Or, and this one might surprise you, we can just ignore the problem.
Yeah, that last one, ignoring the problem, is actually the most common strategy used in desktop operating systems like Windows and macOS. It even has a great name, the ostrich algorithm. The idea is basically that true deadlocks are so incredibly rare in normal everyday use that the extra work and performance cost of constantly checking for them just isn't worth it. It's a trade-off. In the rare case your system freezes, well, you just reboot.
And this leaves us with a really fundamental question in system design. What is the right trade-off? If you're building software for a life support machine or a spacecraft, you would absolutely sacrifice performance to guarantee a deadlock can never happen. But for your gaming PC, maybe a faster experience is worth the tiny risk of having to reboot once in a blue moon. There's no single right answer. It all depends on what's at stake.